and context-free languages. So remember that every kind of machine we are studying in this course is connected or is related to a certain kind of language. And these languages have some particularities, some things they can recognize and some things that they cannot recognize. So context-free languages are more powerful than regular languages, like a subset. So if we draw these sets, here we have regular languages, and here we have context-free languages. We will be writing always CFL, or in the case of grammars, CFG. This is very common way of writing this. So as you can see then, every regular language is in turn a context-free language. So if I ask you, for example, given this language, X, N, Y, M, with M and N belonging to natural numbers. So if I ask you, is this a regular language? What would you say, yes or no? Or you want a
No.
poll? Okay, let's launch a poll. I need a simple generic poll that says only yes or no, because every time I need to edit it, so it takes some time, but let's create it. So what do you think? Yes or no? So this will be the what do you think poll. So is this a regular language, the one that is on the whiteboard? So we have one vote. Some people says no, other people says also no, and maybe we are watching live. Well, maybe you cannot see live, but I'm seeing live your votes. I cannot see who is voting for each one, so you can be safe that your vote remains anonymous. So don't be afraid of making a mistake. You can freely vote. Okay, so we have 13 out of 16 votes. So there are 3 people still thinking about it. Please do vote. One more to go, the last one. I don't know who is he or she, but maybe they are sleeping. Let me see who is suspicious of sleeping. Or maybe it's me. No, I cannot vote. Okay, now everyone is awake. Thank you. Okay, so let me share with you the, where can I share the, okay, yes, share results. You can see here, yes, only 6 people voted for yes and 10 people voted for no. Okay, so this means we need to clarify a lot of things, or maybe the question was a little bit tricky. So I will stop sharing this poll. The correct answer is yes, this is a regular language. So why, maybe why the confusion you have? Because you have 2 indexes, N, M, and N here. And maybe you are thinking we need to establish a relationship between them. But if you look carefully, this is just M and N, and there's no relation between them. Meaning that N could be any value, M could be any value as well. So they are completely unrelated items. Meaning that this could be written as a regular language as this: X, any number of X's, and Y, any number of Y's. There is no relation between them. Of course, if we change this to M is equal to N, for example, adding this restriction or any other M is greater than N is less or equal to N, to M, any of these restrictions of course, immediately when I add any of them, this won't be a regular language anymore. Or even is different. If I say and M is different to N, then the same. This won't be a regular language. However, in this example, we don't have any of this, meaning that I can just replace this for this, because the clean star does not require that they are the same or different or greater or anything. There is no relationship between them. So yes, maybe the question was a little bit tricky, because when you see this M and N belong to N, you immediately recall the last example we saw last time, when you are establishing a relationship between them, and then you would need a stack. Yes, but however, for this language, we do not need a stack. So yes, this is a regular language. Yes? Do you agree now, or not completely? I want you to be completely convinced. Okay, so second question. Now we know a little bit more about this. Is this a context-free language? So again, let's poll. Ouch. No, it's not that one. I need to relaunch. Okay, there you go. So now the question is this a context-free language, the same that we have seen before? And maybe you can hear the garbage collector outside of my house. Okay, we still need 5 more votes. 4, 3, 2. 2 more to go. 1 more to go. That's it. Okay, so I'll share the answers with you. And share results. You can see here the results of this poll. So most people say yes, this is a context-free language, and some people say no, which again, it might be a tricky question, right? So remember, I don't know who said no, so don't worry. This is good to participate always. So I'll stop sharing and then go back to the whiteboard and say, well, why yes? Well, just because of this, because if it's a regular language, then every regular language will be a context-free language. So we are guaranteeing here, because we can write this language as this, that this is a regular language. Therefore, it's in turn, this is a context-free language. So maybe you are answering no, because you don't need the power of the context-free languages to process this language. So maybe you are thinking strictly this is a regular language, right? So maybe in this way of thinking, you would say, well, this is context-free languages. These are context-free languages because we really need the power of automata of push-down automata to process these kind of languages. So yes, your reasoning is correct. However, when we ask that, when we want to be a context-free language that is not a regular language, which is the part that I have here assurated, that I have marked here, then we would be asking, is this strictly a context-free language? And maybe that word helps to understand that. Is this strictly a context-free language? However, just adding a word is like make you perhaps feel how come a word will change everything. Then it's very easy to fail on these kind of questions. So we won't be using this strictly here. So from now on, always we will ask only if it is a context-free language. And if we don't want explicitly to be a regular language, we will say, and is this a context-free language and not a regular language? We will try to do this very explicit in order for you to have very clear that we are talking about this part and not a regular language, right? So if I only ask, is this a context-free language? The answer is yes, because every regular language is a context-free language. Yes? Or confusing? We can launch a poll saying, do you think this is confusing? And you can vote yes or no. But I think it's not that confusing. Okay, so now let me show you how is that every regular language can be a context-free language. And I won't do the demonstration by itself,
Sorry,
but yes.
I have a question.
Yes.
So in this sense,
Please go ahead.
is correct to say that all regular language is are a context-free language?
Yes, all, let's write it like that. All regular languages are, in turn, we can say, or are context-free languages. Yes, yes, it is correct.
Okay, thanks.
Welcome. And that's precisely what we are going to see now, because suppose we have an automata that processes this L, this language L, we have in screen, on screen, sorry, and let's say this accepts any number of n, oh my God, no, any number of x, and then it accepts any number of y's. So maybe we can, it doesn't say it has to be deterministic, so I will take the liberty. Yeah, let's keep the lambda. We say that it was the same as epsilon. And then any number of y's, and then it will be acceptable here and here. So first, do you agree this automaton is correct? Does it correspond to this language?
Which automaton?
Okay.
I think that we are not seeing your last draw.
Oh my God, and I'm drawing as crazy. Okay, maybe because I have opened the poll. Which automata? Yeah, which automaton? Good question. You cannot see it. So let's relaunch the whiteboard, which is not white, it's yellow, so it's the yellow board. Okay, so this is a non-deterministic automaton, an NFA, right? So now you can answer. Let's move this.
Yes.
Yes, it seems it's correct, right? So this is an NFA. So there is a very simple way to convert this into a push-down automaton. You just add, and let me change my pen color. You will need to add the operations on the stack, which are lambda, 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 and lambda, lambda, lambda. Voila, it's here, the push-down automaton. So this is related to the question I had before. Sorry, I couldn't recognize the voice, but I heard the question while I hadn't the camera, which asked, is it possible to have both lambdas here? Yes, you can see here an example for this. And also, can be all lambdas? Yeah, all can be lambdas. And then what does this mean? That you can just change from here to here, ignoring everything. You can ignore your input string, you can ignore the what is on the top of the stack, and you can just not push anything into the stack. And this is valid. And this is the lambda transition, okay? And whenever I mention this, I always remember a very good movie a very good automata movie, which is called The Silence of the Lambdas. So this is a very good movie. And at the end, there is a cannibalistic automaton eating other automata. So it's very cruel. And the lambdas do not say anything because they are just here allowing any transition. Okay, so sorry, jokes apart. Then you can see that, yes, it is possible to ignore one or other, or even, of course, for other automata, you can ignore for a transition, you can take into account only what is on the top of the stack, like, for example, a transition like this. So this is valid as well. We are ignoring here the input string and considering the top of the stack for making the transition. So let me go a little bit deeper on this, and because I want to explain you determinism and non-determinism on context-free languages. So, so far regarding this, I think there are no questions, right? Everything is so clear as the water of Nile River. Good. So, let me ask you again. Suppose we have something like this, and we have a lambda here, but not on the top of the stack. So I want you to tell me, is there determinism here or not? Or is this automaton, this push down automaton, deterministic or not? So yes will be deterministic, no, non-deterministic. Again, Paul. So this is exciting. So far we have a tie, 7 and 7, 2 more votes to go. And the last vote, ooh, complete tie. Let me show you results. There you have, this is nice. This is a nice tie because it means there are a lot of questions. So, okay, I would like someone who voted for no to tell me why does he or she think that this is not non-deterministic. Okay, maybe you are shy, so I will try to read your minds. So you are thinking that because of this lambda, you are not taking into account the input string, right? So you could have something like, here you have the input string and you have x, x, y, x, right? And of course there's the machine here and the stack says x, x, y. So at the top of the stack, you have something like this. You are reading this y. And then you are standing on this state and you need to take a decision. Would we go to this way, x, or we should go this way? And it results, it doesn't matter what we are reading here. We do not care. But we do care on what is on the top of the stack. So the stack is very clear. The stack says, okay, I have a y or I have an x. So despite we are not taking into account the input string, I can take a decision, and it's very clear, based on what is on the top of the stack. So this makes us think, or this allows us to think, that this is not non-deterministic. So it is deterministic, because I can take a decision very clearly depending on this stack. So in this case, despite this lambda, and that's why I'm asking you, because this can be a tricky question. So from now on, now you can recognize that you can take a decision based only on the top of the stack. Yes, to make it clearer, let me put it differently. Suppose that what we are ignoring now is not the stack, is not the input, but the stack. So maybe it's clearer for you if you have something like this. Should I go for X or should I go for Y? Yeah, like this. So I think this example, which is very similar to this one, but I'm taking this, a decision based only on the string that I'm reading, X or Y, it's very clear. Why? Because even if you have any doubt, you can just ignore this part, right? And say, oh, well, yes, this is a deterministic finite automaton, as the ones we already know. Yeah, because we are ignoring completely the stack. And then we know, and it's much more clearer, that yes, I can take a decision only by looking on the input string, X or Y. Yeah. So the same here, just that we are deciding now on the top of the stack. Yes. I don't see you very convinced. So I don't know if the question is too tricky.
I just have one question.
Yes.
And is what about the accepted states?
Oh yes, they are sleeping. Yeah, well, there are no accept state for this example, but well, if it makes you feel better, we can do this. But well, in this case, no, there is no language. There are no strings in this language without accept states, which is valid as well for both the push-down automaton or for the deterministic finite automata. So well, yes, I didn't draw them just because that's relevant example. That's why. But anyway, if you want, we can draw them. Of course, the language changes. Now, let me also make the point that this automaton and this accept a different language. It's not the same, because this one depends on what is on top of the stack. And because this is the initial state, I think it won't be able to follow any of these arcs, because there will be nothing on the top of the stack. Yeah, but these are just particularities, not what I intended to illustrate. Yes? Okay. So let's keep with this, let's put another example with these lambda things, which I think make you a little bit worried. So let's make more examples. What about this? XX and oh, and the accept state, so that you can feel better. And X, Y, lambda. So in this case, the input string is the same. So maybe we can think if this is non-deterministic. So I will ask you again. Yes, too many polls, but I think polls make you a little bit restless. So I insist. Remember, I cannot see who is saying yes or who is saying no, so don't worry.
In this case, the answer yes is deterministic or is non-deterministic.
Oh, yes, yes, yes. Yes. Okay, so now you can see I'm a doctor as well because I can write as a doctor. So we have two people thinking deep inside their minds, but that's good. It's always better to think than not to think. One more, the last one. Okay, so 10 more seconds. Maybe he or she had to go somewhere. Okay, so I will finish the poll and share results. So here, most of you are thinking that yes, this is deterministic, and that's right. So again, maybe the ones who thought that this was not deterministic were concerned by this part, right? That they may say, well, it's because how come you can select a path if you have clearly the same input symbol on the input string? However, let me remind you, like in this diagram, that despite both having here this X, you can decide where to go just by looking to the top of the stack. So it is possible to take a deterministic decision, meaning that this is not ambiguous. So in this case, yes, this is deterministic. So let me annotate the correct answers so that you keep track of which ones were the correct answers. So I think yes, and I think all of them have been deterministic. Yes, so it's yes and yes. Okay. Okay, so don't worry, maybe this determinism is a little bit trickier than before because now we depend on two different things. So if you have doubt, you just think, can I take a decision based either on the input string or the top of the stack? If I have any of them, then I can take a decision. In this case, we have the same here, but you can take the decision based on the top of the stack. And here, you don't care about what the input symbol in the string is. However, you can take the decision based on the top of the stack. And here, you do have the input string. However, you are not taking care of the input stack. Sorry, of the top of the stack, right? So maybe you can think of an OR operation as long as you have the input string or the top of the stack, then you can take a decision. Okay, so let's keep with this. Now, let's make another one. So let's say this. Yeah, so in order to confuse you more. Yeah, so that's terrible, right? I'm playing with your brains. So again, the same question: is this deterministic? Yes or no?
That's
I
the
think
same
that we are,
question again. Yeah. Which automaton?
yeah.
Okay. Sorry, I'm drawing as a fool by myself here. Oh, I see what's happening. This is connected to a different. And what about this? Yeah, that was the problem. Also now the technical problems are worse. I cannot launch the sharing. Sorry for the technical problems of today. There are some days that just go like that, and it's okay. Yeah, we have it. So same poll again. We need some music, as in Kahoot. Okay, only 3 more people who don't want to vote. Maybe you are tired of voting. One more. The last one.
Confused.
Yeah, maybe. Okay. So let's stop the poll here and share results. So most people say yes. But now let me show you the following scenario. Imagine that you have, as before, this X, X, Y, X, Y, and some others. And you are watching this, you are reading this, and of course there's the machine here, and you have the stack here, X, X, Y. And you are reading the top of the stack, which would be this Y. Yes? So now you can see both conditions comply. So you can say, okay, I can read an X and ignore the stack. Then you follow this arc. Or you can ignore the input and pop out the stack and follow this arc. Which one is the correct one?
Both are correct.
Which one?
Like you can go either up or down.
Yeah, right. So that makes this non-deterministic. So you can say, oh my God, when I thought it was, it wasn't. And when I thought it wasn't, it was. But well, yeah, now I think you are training for this. So that's why I like to put several examples, because recognizing non-determinism on person automata it's a little bit tricky. However, with these examples, I think you are having it clearer and clearer. So whenever you have something like this that combines both conditions on the top of the stack and conditions on the input, and have something like this, then you should imagine something that could happen like this situation. Maybe you could argue for this case. You could argue, however, I know that as this is the initial state, that it won't be never a y, yeah, because I'm starting, so the stack is empty. Well, just let me tell you, you can never assume that the stack is empty from the beginning. Yes, just like when you are programming in C. I don't know if you still do that. I hope you do, because it's fun. But when you program in C language, remember that whenever you use a location, a memory location, you cannot assume it's empty. Even if you malloc it, malloc will reserve that section of memory for you, but it won't be empty. There will be whatever it was there. So you can think of this stack as something like that, that despite we are drawing here like there is always how to say a plate, a base, or a support for this stack, it doesn't always mean that we will receive an empty stack. Yeah, just because this is the definition. The definition doesn't say it will be empty as always. And that helps us also to avoid having to think more, because we don't have to think, well, yes, this is the initial state, and then this way won't be never followed, because this is not possible to have, and then this is, because you know what? This is kind of trying to think at the execution moment. Do you remember when you are doing syntax parsing, any compiler that does syntax parsing, it can tell you this variable, for example, you define something like integer I, yeah, and then you assign something like I equal pi or something similar. So at this moment, it will be clear that you are just making a mistake. This is a syntax error, because you are defining here an integer, and then you are trying to assign a floating number like this. However, there are other errors that are much more difficult to identify. Like, for example, what should your interpreter do if you have the same I, but you do something like 5 divided by 2? So the strategies will be different here depending on your language. For C, it is clear that it will cut the decimal part. But for other languages, maybe this will raise an error. And which one is the correct one? Well, we don't know. So we start having some semantic clashes, some semantic kind of errors, because this is not so clear what we do, because it has to do with some kind of meaning. Yeah, so we try to keep to the syntactic level as much as we can. That is why we do not try to analyze these kind of things in this for this example. Yeah, so in short, TLDR, never assume that you have an empty stack for this. And also, and it will be even more evident when we see Turing machines, we cannot assume that our tape, it will be empty. We just need to know where we will start our execution, but we don't assume that our tape is empty. The same here. We don't assume a lot of things, okay? Well, okay, so one last, and the last one on determinism and non-determinism. So the last poll. Okay, time over, or we have a sleeping student because we have been doing the last polls with 15 votes. Okay, so in this case, by unanimity, everyone said yes, because for this transition, despite is just ignoring here what is on the input string, is not considering anything, and just adding a hash to the stack. And in this other case, sorry, in this next arc, we are just consuming it and then pass to this one. So the language that will be accepted by this automaton will be only the lambda string, right? Because if there is something different, we won't be able to consume it ever, because we are never reading from the input string. So if we had something like A, we can assume that here it will go to the pit, and we need to consider all those options, but the pit will never finish reading that. So the only possibility is just to accept lambda. And then as there are no other options here, it seems the only option is just to follow this one, and then here the same, just to accept, to read based on what is on the top of the stack, and finally get here. Yeah? Okay, very good.
So we have a question.
Yes, please.
For example, in this automaton exists the possibility that in the stack exists a hash. I mean that, for example, you say that the stack never when is never assume that the stack is empty. So in this case, we have the possibility to exist a hash in the stack. Yes.
Yes. So suppose, for example, you have something like this, right? And the top of the stack is this, and maybe you are wondering if there is already a hash in the stack. Well, it doesn't matter, because it says we don't care what is there already. You just put a hash inside. Then what will happen is that you are adding a hash on top of everything that is already here. And then the second one, you will be just consuming this one and then accept. Remember that for accepting a string, you don't need to empty your stack. That's never a condition for accepting a string. Only if you want to evaluate if you go back to the same state as the one you received your stack from, then you use this additional hash. Yeah, but it doesn't mean that down there is something else. You don't know. I don't know if I answered your question, Emilio.
Yes. So thanks.
Yeah, welcome. So more questions here on deterministic and non-deterministic. Okay, so let's, not now, but maybe one day let's do more exercises for identifying deterministic and non-deterministic push-down automaton. For now, I think it's enough. Otherwise, our heads will start to ache. So I don't want you to have so much pain on this. Okay, so let's change completely our subject so that we have something refreshing, I hope so. So now we will see the famous CFG, the famous context-free grammars. That they are very important, and probably you have heard of them already, because most programming languages define their syntax using a CFG. When you see perhaps the definition of C, they will be using something called Backus-Naur form. Okay, so let's, now I like this font, so I will be adding everything using this font. So can any of you tell me what is the Backus-Naur form? Let me try to quickly find an example for this before getting on. Even for learning Java, you should have come across something like this. But as I don't like Java, I will project this. So this is Backus-Naur form. As you can see here, this is it okay, or should I make it bigger?
Just can see it that way.
Okay. Well, if you are in a device that makes it look so small, please tell me. Okay, so this is a context-free grammar, and all syntax of C is here. You can see it's a bit complex, not that complex, and this was published by our idols, well, or maybe only my idols, but it should be your idols as well, Kernighan and Ritchie. We talked already about them a little bit, and we started telling about Unix systems and everything that they did, and particularly, well, they defined the C language. And well, the C language, you already know it. You can see here then the syntax in Backus-Naur form. What does it mean? Well, the Bacchus-Naur form is using this kind of pipes, which are already mean or, and instead of an arrow, they are using these 4 dots and then equal. But actually, what this means is storage class specifier produces an auto, or this produces a register, or this produces a static, or this, etc. So you became a little bit familiar with this when we at the exam. Do you remember the question that asked which one of these produces words C22? Do you remember that question? Well, that was also in Bacchus-Naur form, or almost, because it used arrows here. Also, the Bacchus-Naur form allows some optional things like these ones, but these are working also as to enclose what is inside. So you can see also here a clean star, and also you can see something which is a plus star, which is not more than a clean star starting from 1. Instead of starting from 0, the plus here starts from 1. And well, we can keep reading this, trying to understand, but what I want just to point here is that Bacchus-Naur form is, or was, I don't know, I think still is useful, a popular way for defining languages. So whenever I ask you, please define a new language that processes XYZ, what one is expecting is to see this kind of definitions. So this is a context-free grammar. All languages are defined by using a context-free grammar, not a simpler one. For simpler, I mean not a regular grammar, because most or there are some things that need to be stacked. What kind of things? Well, you can put an if-else sentence inside an if-else sentence, inside an if-else sentence, etc. And this could be infinitely done. So with a context-free grammar, we have a stack, and the stack is very important to have this mechanism. The stack will allow us, let me be redundant, the stack will allow us to stack several constructions of the language several times. That's why all syntax of languages or formal languages is defined, or all syntax is defined by using context-free grammar. So, and the way of writing this context-free grammar is very popular to use the Bacchus-Naur form. So Java has its Bacchus-Naur form definition, any language you want. And sometimes just by looking the Bacchus-Naur form, you get a grasp on how is this language working. Sometimes you can learn how to program certain things, certain structures, just by looking at this Bacchus-Naur form. Okay, so enough for this. Not only C is defined as this, maybe you can find other, particularly those that have structures that can be nested. If you have seen maybe assembler, assembler very well and like it and enjoy it and every day do everything in assembler. Assembler doesn't have a very complex syntax, right? Because you cannot stack things in assembler. I mean, you will only start just like having a certain memory address, and maybe try to load some register or change from AX to BX or something like this. But you don't have like these kind of things, right? Brackets that allow you to go back, etc. Or even you don't have things like begin or end as in Pascal. So let me draw this more in a more structured way. So when you have languages that are structured, do you remember the paradigms of programming languages? No. Yeah, I know, because I always ask this and nobody knows, so don't worry. But it was something that was taught, I think, more before than now. However, these paradigms still exist. So let me make a little bit of a parenthesis here. So paradigms of programming languages.
I remember some paradigm, but not all.
Yeah, please go on.
Well, for example, the object-oriented. I don't know how do you say the sequential paradigm, or I mean that it's a normal.
Yes.
Let me remember all, but I don't remember very well.
Don't worry, don't worry. But yes, maybe at certain point of your studies, you have come across of this with these things. So the most, the simplest one is the imperative, which is like assembler, like here, or things like basic. I don't think you know I don't think you know basic, but it was very basic. So you say something like print hello, and then line 20, good to 10. Yeah. And then it prints hello, 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 and that's it. It's very similar to the structure of assembler because these look like addresses, and maybe you have 4 and next, but it's very difficult to have them nested. You don't have subroutines and things like that.
Isn't it what is called spaghetti code?
Well, it was the way we coded in the 80s. Because there, of course, there were structured languages like this one, and let me write here structured. Yeah, and of course nowadays I think C has this kind of good too, and they say always avoid at any means using a good to in C because you would be regarded as a very, very bad programmer. Yeah, but it was maybe when the transition came. You cannot avoid these good tos or jumped. Maybe they look more elegant in assembler if instead of a good to we have something like jump if not 0 to address 000A. Yeah? But it's a good too. It's the same, a conditional jump here. It's the same. So you don't have these kind of structures here. The structure things mean using brackets here as in C or Java, or in Pascal, begin, end. And these kind of things became popular well, in the States around the 80s and maybe at the end of the 80s in Mexico. And the imperative, well, was much more before. Of course, there were other ways of programming, but for example, if you see the first versions of Fortran 77 or so, they were imperative, like almost no structure. Nowadays, Fortran is a structured languages. Another example of imperative languages is COBOL. Have you heard of COBOL, ALGOL? So this is prehistory. Yeah, I know, but maybe you have heard of those very ancient languages. Well, yeah, so when structure came around the 80s with languages like C, it was like, wow, now I can structure my programming. And of course, yeah, I can avoid spaghetti programming. So yeah, structured programming is much more healthy for us. It allows us to understand much better, but it's not the only way of programming. We have at least other two, and let me, object-oriented programming, yes, it's a paradigm, but we have also other two different paradigms. It's difficult for me to say that. So we have the functional paradigm. And this is very important because we will be using, if we have time, so we should go faster maybe, we will go into functional programming. And it's another way of thinking. You have to think things differently. You don't have a for here in functional programming. You don't have a while and other structures. You have to think on lists, for example. So Can you tell me? Can you tell me if there is a language that you know that is based on lists? I'm always giving you the answer. Which programming language is based on lists and sounds very similar to list?
I've heard of a language called Lisp and all the memes about parentheses.
Yeah, good. Right. Yeah, yeah. So it's terrible, right? The functional programming looks like this. And yeah, it's terrible. Sometimes it makes it pretty unreadable. Yeah, and the memes are very nice. Like, look, these are the parentheses that your grandfather used when he used to program, and a bunch of parentheses. Yeah, so it's a lot. But we will get into functional programming a little bit. It's based on lists. And this is also very old. This coexisted with imperative languages. So we are speaking about the 60s here. So Algol 60s, COBOL 60s, BASIC 70s, well, assembler code, I don't know, 50s, and structured 80s, and Pascal also maybe 88 or something. Pascal was very popular by that time. Nowadays, no one remembers Pascal, but it was the programming language used to teach people. Well, so there is another paradigm which is sometimes ignored, which is the declarative. And there are not so many examples of declarative programming. Most logic programming is done, is declarative. And there is one programming language which is very famous for this. So now that I said logic programming, maybe can you tell me an example of declarative programming? It ends with log of logic. And it starts with something like programming in logic.
Prologue,
Yeah, right. Muy bien. So the example here, well, I didn't note it here, Lisp, and of course here we have Prolog. And Prolog is crazy as hell because we are used, at least in functional languages, that we have a function and we have an input and we will have an output, right? Well, in Prolog, you make some declaration and the variables unify so that sometimes your output is at the input and at the arguments, because the arguments, which are variables, unify with other parts of the logic. So again, you have to change your mind to program in Prolog. And this is not so new as well, but not so old. We are speaking about 80s. And well, finally, object-oriented programming, which didn't change the game that much, but we are still using a lot this kind of programming, and it's a lot of C++, not C. C without plus is not object-oriented, despite we have structures and something like that. We don't have objects. And of course, the terrible Java. Yeah. So Java is nice, but it's I don't know, it's like they say that it's like a scorning auntie that is always scorning you. You should declare the exception and you didn't, so I want to run. So just doing a print hello world takes 15 lines because you have to do the exception. What if I cannot print to the screen? Then I have to inherit the exception from the general set of exceptions. Well, yeah, it helps you to properly program. It's very difficult to have bad practices in Java, but it's very scolding one. Okay, so this is object-oriented programming, the one you are probably most familiar with. And in the 1990s, it was the bomb, right? Everyone was talking about, have you heard about the new way of programming, which is object-oriented programming? No, I haven't. How is that? And well, yeah, Java is much more object-oriented programming than C, C++. C++ still has some violation of object-oriented programming. So Java is very pure in this sense. So well, despite I don't like Java, but I recognize it's very good for large projects because of this. And I think that's one of the reasons this is very, very popular. And well, after that, I don't know, we have Python, and with Python, we have a little bit to go back to structure because you can do a lot of Python without using objects. You are not forced to use objects in Python. So we go back to structured, and sometimes even we don't use this and we just use indentation. And using indentation for blocks, it was very Fortran 80 something. Well, so it depends. You program on whatever you like the most, but I wanted to talk to you about this because any of these languages has a grammar, a formal grammar. And despite being so different languages, all the grammars for these languages can be expressed as a context-free grammar. And probably you will find a Bacchus now form. Yeah, even those strange ones, such as Lisp, if you search the web for Lisp context-free grammar or Lisp BNF, you will find a definition for Lisp in Bacchus now form. Even the same for Prolog. So with
what about fourth?
Fourth is this one, right? Fourth, I think it's.
Yes.
I don't know very well for it, just know it's maybe 50 something, maybe. I think it's close to these ones, but I don't know it very well to know. I don't know if you know a little bit more of Fort.
I've tried to learn about it, but it was difficult.
For sure, there should be some history of programming languages over there in the internet. But yeah, it sounds to me like this family of strange languages now defunct. Fortran is not dead. Particularly, Fortran got its last kick recently with massive parallel programming computers. Just before the GPUs. When the GPUs came in and the tensor processing units and all that, Python became king because most of the libraries like Keras, TensorFlow, and all those are implemented in Python. So most people who are thinking on programming in parallel at the GPU, TPU style will use Python. But before that, I think was a rising called vector programming, which is similar to the concept of tensor, but tensor is like more multidimensional. And at that small time in history, which was like 2005 or something, it didn't last too much. Fortran was becoming the language de facto for doing these kind of things. So nowadays, Fortran, I think, is kind of dead again, but well, it has its last kick. And of course, it depends of who is using them. Probably if you go to CERN or some place where they have been using Fortran for decades, they will still use Fortran because of the developments they have. Well, but this is not programming languages class. So let's go back to our dear automata. And particularly, well, all this came into the scene because of the context-free grammars. Now I want to color them in different colors. So this came into scene because of context-free grammars and why they are used a lot for processing syntax. And that's why before I said we don't want to deal with the semantic part because that semantic is very difficult. It's you know, in a compiler system, you have lexical analysis. Probably you have seen this before, but it's analysis. No, right? Analysis. Oh, not right as well. I cannot spell analysis anymore, so I will just say. And then we have syntax analysis. You see, it's getting worse. please someone help me with analysis because I'm really lost. Just at this moment, I don't know, sometimes it happens to you that I think,
It's okay.
yeah, I was right? Okay, so if I write something very ugly, you tell me, please. So first you have lexical analysis, syntax analysis, and then you have semantic analysis. And these are the phases for any compiler. So interestingly, these phases tried to be imitated for natural language processing, where lexical analysis is performed within morphological analysis. Syntax analysis was the same, and semantic analysis was the same. Even despite I'm writing morphological analysis, well, sometimes it's called as well lexical analysis. So what is lexical analysis? Well, you go inside each word and you identify the parts that conform this word. For example, if you are using a plural or not, like in word or words, or if you are using some kind of conjugation like play, plays. And of course, you know, in Spanish is much more complicated because there are a lot of ways of conjugating jugar. Yo juego, tú juegas, él juega, nosotros jugamos, ustedes juegan, etc. So that conjugation is also a morphological analysis issue. And of course, other declensions we have in Spanish, like diminutive forms, like amorcito for amor, or I don't know, lapicito, etc. And other languages that even got much more complicated because they have cases for everything, the genitive case, the dative case, and I don't know, the vocative case. Surely Oksana and Dima can tell us a lot more of this case. And this is also morphological analysis. So just for curiosity, Ukrainian, how many cases has? 6, 7 declension cases?
I believe Ukrainian has 7.
7.
And not sure about Russian.
I think 6. Oksana, do you know?
I don't understand which case.
Подержи, Оксана.
Yeah, 6.
6, okay, so 6 for Russian, 7 for Ukrainian. And well, if you sometime try to learn Russian, you will become crazy because as we don't use them in Spanish, we are not used to think in that way. So what we don't have in our language, I think sometimes it's more difficult to deal with. But we do use cases, however, use preposition to differentiate cases.
There are also like for these words like he, she, like his thing, he something, to like do something with him. There are traces of this thing in English.
Yes, a little bit like him. You don't say I'm doing this with he, but we have to change the pronoun to him. That's a case of declension, of changing the depending on the function the word has. You have to write it differently. Okay, so okay, let's don't go too deep into this. And then we have syntax analysis, which will tell us theoretically which sentences are grammatically correct or not. And here we get into big deal of trouble because you know that linguistics don't work like that. Sometimes we can speak very badly and people will understand, and sometimes we can say, but you understood me, so what's the use? I don't care, right? And yes, sometimes the syntax is completely wrong. However, the semantic context is kept. So apart from that, there are a lot of things that sometimes it's not clear which is correct and not syntactically. Also, I won't go into much detail on this, but syntax analysis analyzes as the example of the last class of John skates, Mary skates, John hits Mary, Mary hits John, and at the end they end up very angry. They were very happy, but they got angry because just going to skate and it became battle. So that was a way of doing syntax analysis. So what I'm trying to do here is just to map that analyzing a formal language and the way some people has, or a lot of people has tackled natural language processing is almost the same way. Yes, so we tend to have these kind of different tools, and traditionally lexical analysis is performed by following a regular language. And syntax analysis, it is said that it can be performed doing a context-free language. So then we start matching these different things. And for semantic analysis, well, we don't know, but probably it won't be a context-free language, but we need a lot more different mechanisms to grasp semantic elements. So I could say maybe if we want to force this thing, we will have a phrase structured language. Yes, but this is like a dotted one because this is not so standard. We can say, yes, this part is very classic, this is very classic, and this is also very classic, but this is not so classic. So the people who try to study languages are concerned with semantics, but they won't say, or not everyone would say that this is tackled always with a phrase structured language. Okay, so I'm doing a little bit of spoiler here because we have seen already regular languages, context-free languages, and we will see when we finish this chapter, we will see phrase structured languages and Turing machines. So this is like a general overview. Each time languages are more powerful than before, and they include the language before. So as we saw, every regular language is a context-free language, and you will see that in turn is a phrase structured language. So regular language is this, and a context-free language will be also a phrase structured language. We will see that later. So now that we are then seeing this, we will close this part just by saying syntax analysis then is performed by context-free languages, both for formal languages and for natural languages. So this is a very classic way of working. Nowadays, if you want to use natural language and get even into semantic analysis, each time using grammars is becoming more and more rare. So we use things like word embeddings and things that try to approximate meaning, but not consider meaning as here as a formal language. Well, and finally, semantic analysis, what does this mean for a formal language? It means translation into machine code. If you program something in C, then when semantic analysis is correct, then it is able to translate into assembler. And that's it. Well, yeah, enough of a lot of theory. Sorry for getting too deep into this. Well, so all this is just because we are starting to see, we have some chat. And I cannot see. I have too many windows. And chat is terribly behind something. After spending 30 minutes. Okay. Sarah says SQL. Nice. And a picture of SQL.
The picture is Dimas.
Oh, okay. And Sarah says SQL. Okay. Well, maybe fourth is further BNF. So let's keep doing research on this. Like, I don't know if you know this language is called mini macro. And perhaps if you ask Dr. Gelbuch, I think that works also like very crazy, just mixing different symbols. Maybe that doesn't have also a BNF description. So please ask Dr. Gelbuch about mini macro. Maybe even he invented this language, but it sounds to me very similar to this thing you say of fourth. And Sarah says SQL. Can you please tell us about?
Was in the past term about the declarative language.
Okay, okay. Oh, good, 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 good. That's very nice. Let's write it here, SQL. Yeah. And I several times forget about this, but yeah, thank you very much, Sarah. And SQL can be very, very difficult to interpret sometimes, even for the server. When you overload the server with inner join and outer join SQL sentences, you can kill your system with that. But SQL is very nice when you can visualize, or not visualize, when you implement something that works well by mixing a lot of tables. It's a very nice language, not so optimized, but for those kind of things, but very, very nice. Thank you, Sarah. I'm sorry for not seeing your chats before. If you see that happens, and sometimes I'm skipping to a new theme, please let me know. Okay, so yeah, grammars. So a context-free grammar is very similar to the grammars we saw before. You remember we have a non-terminal at the left side, and at the right side we have a set of terminals and non-terminals like this, right? And we had some canonical way of writing a regular grammar. For a context grammar, we won't have a restriction here. Of course, it can be written in a simplified way, but in theory, a context-free grammar can be just any sequence of terminal and non-terminal symbols here. And as long as it complies with this, that there is a series of terminals and non-terminal symbols at the right side, we can say it is a context-free grammar. And we can guarantee that there is a push-down automaton that can process that grammar, right? So differently to this, we can have a regular language that has a similar way of representing this. However, in order to demonstrate that this is a regular language, we need to convert it to the canonical form. And sometimes there are some constructions here, like for example, T and I don't know, T and M, T. If we do something like this, oh my God, sorry. If we do something like this, then we won't be able to convert this to the canonical way. So I know that this, and of course we need N goes to something. Just because I'm inserting here this M, and M is the same M here and has something before and has something afterwards, then this is not a regular language. So sometimes in order to demonstrate that, or to show that a regular language, a regular grammar is, or that a grammar is regular, we need to be able to convert it to the canonical form. Whereas for a context-free grammar, we don't need to do that. This, just by looking at it, yes, this is a context-free grammar. Yeah. And lastly, because time is running quickly, I like this. Time flies like an arrow. Because this phrase is very ambiguous syntactically. You can say that there is something called time flies, that this is the adjective modifying this noun, and then you have a noun here, which are time flies, and then this is the verb, and an arrow is another noun phrase, and then we have here, this is the subject, and this is the predicate, and this is a sentence. Yeah, so this is one way of interpreting this, like time flies like an arrow. So in Spanish it would say something like las mosquitas del tiempo, a las mosquitas del tiempo les gusta una flecha. Just because I am applying rules for parsing this, syntactic rules, wrongly. While the correct way of interpreting this should be, let me copy this. Well, sorry, it would be a little bit cluttered, but we are in a hurry. The correct way would be time is a noun, flies should be the verb, like is a complement. What is like here? This is the NP, and this is flies, like. I don't know if someone can help me with likes, but it's something like this. So this would be, these three is the predicate, and this is an NP, NP, BP, this is a sentence. So if we do, sorry for not knowing what it's like, but this says into translation, el tiempo vuela como una flecha, which is the correct interpretation. So just I wanted to quickly illustrate that it depends very heavily how you do the syntax of a sentence, how you parse a sentence syntactically for having the meaning. That's why we are so afraid of going into the semantic thing. So we stay at the syntactic part. Okay, so I still have 10 minutes. Sorry for deviating too much, but I hope you find it a bit interesting. So let's define, or let's use this grammar. This grammar is defined and mentioned a lot of times in the Brookshire, and it says A, N is B, and B, M goes to lambda, and N goes to lambda. Yes, so this grammar produces strings of the type Zaza. That's why we called with our dear grammar Zaza, because we will be using it a lot of times. So why Zaza? Well, because we have something like this, and we will try to obtain, just as before I did with time flies like an arrow, I'll try to obtain S. Will I be able to do that? Probably no. I should. So what do we need? Well, we first need to take this. I think I copied it incorrectly. Let me. Yeah, it should be wrong. Give me a second. Yes. Sorry, my bad. Instead of lambda, this M and N go to Z. Okay, now we are able to do the following analysis. So this Z would be converted to M, and this Z would be converted to N. Why not the opposite? Well, just because we know that will guide me or will take me to an S. Of course, this is ambiguity, and we will see next classes how to deal with this ambiguity. Now that I have this, I can parse AMA, and we know that AMA goes to M as well, so this will be M. And also we know that BNB goes to N. Why? Because of this rule, yes? And finally, we have Z, M, N, Z, and this is the first rule. this one, and this will lead me to S. Okay, so we were able to parse this string into S. And if we examine it further, we will see that this M should be in turn more A's. So it can generate something like Z, A, Z, A, B, B, Z, B, B, C, something like this. We can keep inserting as many B's, as many A's as we want. And also these will be independent. If I add here 100 A's, I need 100 A's here, but I can put here just one B and one B here because this and this are independent. So you will have time to play with this grammar at home. You see, instead of playing with your pet, you will play with a grammar, and it's fun as well. And what I want to show you before the class finishes is how to build a push-down automaton from this grammar. Yeah, you see, so just how to obtain an automaton from a CFG in 5 minutes. And it will be literally in 5 minutes. So let's do it. First, I will need space. So I will reduce this. That's the advantage of having this kind of tools. I enjoy this very much. I can do this during the classroom. So, well, of course, I also like to see you personally, but the whiteboard is very nice. So, how to do this? First, add a state, and this state will insert the hash into the stack. Then you will add an S into the stack. And then we will have a very big state just because we will have a lot of arcs coming in and out of it. And we will go back to that. But on the meanwhile, the last state will be an accept state, and we will be taking out the hash from the stack. And then we will just add for every symbol in the alphabet, which for this case is A, B, and Z. For each one of these symbols, we will add a rule that says if you see a Z on the string, on the input string, you will pop out a Z from the stack. If you have a B in the string, consume it, and also consume a B from the stack. And as you probably guessed, you will do the same for A. So it's very easy. That's why it's fun, because it's nice and you don't have to think. And then for each one of the rules, you will add the following arcs. First, you will add, here you won't care about the input string. So it's lambda, and then an S is read, and then ZMNZ is written, is pushed into the stack. For the second rule, we do the same, AMA. For the third rule, which is this one, we will do the same, N, lambda, N, and then BNB. And finally, for the last two rules, lambda, M, and push Z, and lambda, N, and push Z. And that's it. You see, we don't took even 5 minutes to process this. So this is a good news, that you can always convert any context-free grammar into a push-down automaton by using this very simple and effective method. So if you want to buy this, you need only to deposit $59.99 to my account, and you will be able to convert any grammar into a push-down automaton. Just if you call in the next 5 minutes, I can make you a discount of 30%. So call now. Okay, so it's very easy and straightforward, fortunately. And the bad news is the reverse process. It will be very, very cumbersome. Not difficult, but cumbersome. So don't worry for now. Just let's enjoy the joy of this conversion way. And of course, next class, next Tuesday, we will evaluate how this is working, because probably you see, I don't believe you. So that's why I'm telling you right now before I explain it to you, because once I explain it to you, probably you won't buy it. Now, the problem with this is ambiguity. And you will see, we will see also different ways of dealing with ambiguity. Different strategies, and we will see some parsers that look ahead for knowing which is the correct rule to apply, but they will be in the future. For now, this works also as a demonstration that any context-free grammar with this with a single non-terminal symbol from at the left side and any combination of terminal and non-terminal to its right, it will be accepted by a push-down automaton, and in turn, it will be a context-free language. So enough for today. Today I have talked too much, sorry for that. And probably let me ask you some exercises so that you don't forget me during the weekend. Okay, so let's you you will dive into the realms of ambiguity with exercise, well, page 99, exercise 2. And exercise 2 and build. This will be very easy. A push-down automata with grammar of exercise 2. So exercise 2 says that it takes you to appendix C. So more than doing a lot of exercises, you will be reading a little bit on your side. And this reading will consist on learning about ambiguity. Yeah, so exercise 2 says this. And I want also you to deal with exercise number 1, now that you are learning about this. Yeah, so here it says see appendix C, section C1. And so you need to read this and work a little bit into this part. It's not that difficult, don't worry. And then we will come into class with this part. Then that will be 2. Then the exercise number 3, build a push-down automaton with the grammar, with this grammar. So you will do it in 2 minutes or less. Well, if you do it pretty, maybe 5-10 minutes with beautiful circles. Yeah, like this one, perfect circles. Okay, and show that each string, this number 1, derived from a context-free grammar by a leftmost derivation, can also be derived by a rightmost derivation. So more than doing this show, if you can show it, well, it's okay, but I think it's a bit difficult for you to come up with a demonstration. So what I want you to deal with is that what happens. And now I cannot move this. Yes, I can. Okay, sorry for cluttering this board, but what I want you to do is see this grammar, right? It's small, but you can see it. And sorry, I have -1 minute left, but I will finish them. So see this grammar. And I changed at the same time this Z and this Z. I changed this Z for M and then this Z for N, right? And I did it in a single step. But these three can be built differently if we do this first for this Z and then in the next step for the rightmost one. So I want you to try to obtain this S just by going first, only replacing the leftmost part and then going for the rightmost part, and just to be conscious of that. And you can see the same for this structure. Try to think this is if, condition, then sentence. You can try to parse this one by using different strategies. And you will find something like, as this one, like time flies like an arrow, in which it depends on what you are parsing first, you can end up with different trees. So this is what it's about. Yeah. So don't worry too much about this word that it says show. So I just want you to read or examine a little bit on that, to elaborate a little bit on this. Okay. Well, so exercises number 2 and 3 are very clear, and number 1 is just elaborate on this. Not too much, don't worry. No need to do a lot of elaboration within this. Okay. Well, so enough for today. Thank you very much for being here, for listening to me, and I hope you have a lot of questions and doubts. So, keep in touch. Take care. See you.
Thank you.
Thank you. See you.
Thank you.
See you. Thank you.
Thank you. Bye-bye.
Goodbye.
Thank you.
Thank you. Goodbye.
Take care.